Dear students, welcome to the 16th online class of Control System Engineering. In last class, we started chapter 6, which is about stability of a system. In this we study various methods through which we can find out stability of a system. In this we define stability on the basis of natural response, bibostability, and stability with poles location. After this, we studied necessary and sufficient condition for stability of a closed loop system. Whenever a system fulfills necessary conditions of stability, yet after this we can't guarantee whether the system is stable or unstable. To exactly comment on stability of a system, we are interested in the poles location. For a system of first order or second order, it can be easily determined from the poles location. For a system of higher order, we use Routh Hurwitz criteria. Routh Hurwitz criteria give us distribution of poles of a closed loop system among left half plane, right half plane, or j omega axis. This method gave us an idea in which plane the pole will be lying, but it won't give the exact location of the poles. Now we will start. Dear students, after this lecture, you will be able to find stability of a system with the help of Routh Hurwitz criteria. In this lecture, we will also discuss the special cases of Routh Hurwitz criteria. First case is when first element is 0 or an entire row of 0 occurs. Dear students, contents of the lecture are: we will start with some special cases of Routh Hurwitz criteria. First case is 0 in the first column of Routh table, and we will solve this with the help of Epsilon method or with the help of reciprocal polynomial. Second case we have is when entire row is 0. And last topic of this lecture is stability design with the help of Routh Hurwitz criteria. Dear students, we are studying stability of a closed loop system with the help of Routh Hurwitz criteria. This method consists of two steps. In first step, we design a Routh table, and in second step, we interpret the table, through which we find out distribution of poles. In this method, few special cases also occur while computing the Routh table. First case we have is while computing the Routh table is when 0 occurs in first column of the Routh table. As we know that element of first column is used in calculation of upcoming rows, so we will study how to avoid this and get the result about the stability of a system. Second case we have is when an entire row of zeros occur in the Routh table. Dear students, now we will start the first case when 0 occurs in the first column, and we will study the method how to find stability for such cases with the help of Epsilon method. In the given example, you have to determine the stability of a system with the help of Routh Hurwitz criteria. The closed loop system is represented by transfer function T of S. As we are interested in the poles distribution, so we will use denominator of transfer function t of s. Here the denominator of the transfer function is represented by polynomial p of s, which have the highest power of 5. So we will make a Routh table and label each row with Laplace variable s, starting from highest power, which is 5. First row will be labeled as s5, then s4, then s3, and up to s0. Now we will place the coefficients in first two rows of the Routh table. Upon calculation, the coefficients or elements for third row, we get a 0 in first column. Now if we calculate values for row corresponding to s square, we will get a value of infinite, because any number divided by 0 equals infinity. Now to overcome this 0, we will use Epsilon method. In this method, the 0 is replaced by a epsilon, and using epsilon we will complete the table. And the complete table for the closed loop system is shown in the slide. Dear students, after completing the table with the help of epsilon, now we will begin interpreting the table. As we have assumed that epsilon is a small number, it can be positive small number or negative small number. For both cases, result will be the same. In table 6.5, we have first column of labels corresponding to S5 to S0. Then next column is the first column of the Routh table. And for this column, we have to determine the algebraic signs when epsilon is a positive small number or negative small number. You can assume epsilon to be a positive number. It can be 0.001. And for this, if you calculate the column, you will get signs shown in the third column of the table. And if you assume the epsilon equals a negative small number, which can be minus 0.001, and you have to calculate the signs for this value of epsilon. Now for finding the system stability or the poles in right half plane, we will find the sign changes corresponding to each value of epsilon. If you look at column 3 of the table, from row 1 to row 2, we have no sign change. From row 2 to row 3, we have no sign change. From row 3 to row 4, we have one sign change. And from row 5, we have a sign change. Similarly, from row 5 to row 6, we have no sign change. So for positive value of epsilon, we have a total of 2 sign changes, which means 2 poles will be in the right half plane. Now if you look at column 4 of the table, from row 1 to row 2, we have no sign change. From row 2 to row 3, we have one sign change. From row 3 to row 4, we have one sign change. From row 4 to row 5, and then from row 5 to row 6, we have no sign change. So using negative value of epsilon, we have a total of 2 sign changes, which means that 2 poles will be in the right half plane. Now it's a choice of student whether he uses positive value or a negative value of epsilon. For both values, we have the same result, that 2 poles of this system will be in the right half plane. So this system is an unstable system. Dear students, second method or alternate method to find stability of a system using Routh table with having 0 in first column is reciprocal polynomial. The reciprocal polynomial is a polynomial that has the reciprocal roots of original polynomial, and the distribution of roots among left half plane, right half plane, or imaginary axis is the same. Taking the reciprocal polynomial of the root value doesn't move it to another plane or region. Thus, if we find a polynomial that has the reciprocal roots to the original polynomial, then it is possible that we may avoid 0 in the first column of the Routh table. For instance, consider a system G of S equal 1 over S plus 2, where its roots will be defined by polynomial of denominator, which is P of S equals S plus 2, and its roots or poles will lie at S equals minus 2, which is the left half of S plane. Now its reciprocal polynomial will be P of S star equal S into P of S inverse, which means substituting or replacing S with 1 over S in the original polynomial P of S, and the root of reciprocal polynomial will lie at location S equal minus half. So the pole of original polynomial and reciprocal polynomial both lies in the left half. Students, now we will study how to make a reciprocal polynomial. Reciprocal polynomial have roots reciprocal to original polynomial, and this can be simply found by writing the coefficients of original polynomial in reverse order. If you look at equation 6.3, which is s power n plus an minus 1 multiplied by s power n minus 1 up to a naught equals 0. Now in this equation, replace s by 1 over d, and we will get equation 6.4. Now further simplification or factoring out 1 over d whole power n, we will get equation of the form 1 over d whole power n multiplied by a reciprocal polynomial equals 0, as shown in equation 6.5. So the polynomial with reciprocal roots is a polynomial with the coefficient written in reverse order to the original polynomial. Now we will solve the last example with the help of reciprocal polynomial. Dear students, now we will solve the example of 0 in first column with the help of reciprocal polynomial. T of S is the transfer function for the given system, and polynomial for denominator P of S is given. Highest power of the polynomial is 5, and it is s power 5 plus 2s4 plus 3s cube plus 6s square plus 5s plus 3. In this case, we were having 0 in first column, so we will solve with the help of reciprocal polynomial. Its reciprocal polynomial will be found by simply writing the coefficients of original polynomial in the reverse order. If you see polynomial d of s equal 3s5 plus 5s4 plus 6s cube plus 3s square plus 2s plus 1. And now we will compute the Routh table. Table 6.6 shows the complete Routh table for reciprocal polynomial. Now for stability, we will look for sign changes in first column. From row 1 to row 2, there is no sign change. From row 2 to row 3, no sign change. From row 3 to row 4, no sign change. From row 4 to row 5, there is a one sign change. And similarly, from row 5 to row 6, again we have a sign change. So in this case, we have two sign changes which corresponds to two poles in the right half plane. So our closed loop system is unstable system. Dear students, second case for Routh Hurwitz criteria is when entire row is 0. We will study this with the help of an example. For a given closed loop transfer function T of s, we have to determine stability of a system. We will form the Routh table using polynomial of denominator d of s. If you observe second row, we can multiply this row by 1 over 7 for simplification purpose. And if you observe row 1 and row 2, both are multiple of one another. So this causes a row of 0 in row 3. Now for this row of 0, we will follow the procedures in upcoming slide. Dear students, now to overcome this row of 0, we will form an auxiliary polynomial. The coefficients of this auxiliary polynomial will be the entries of row which is above the row of 0. This auxiliary polynomial will start with the power of s labeled and continue by skipping every other power of s. In this case, row of 0 has occurred with a row labeled with s cube. Directly above this row of 0 is a row labeled with s4. So highest power of our auxiliary polynomial will be s power 4 and its coefficient will be first element of the row, which is 1. Now second coefficient will be 6 and we will skip every other power of s, so the term will be 6s square and last term will be 8, so 8. So p of s will be our auxiliary polynomial. Students, now we will differentiate this auxiliary polynomial with respect to s and replace the coefficient of differential polynomial in the row of 0. So new entries corresponding to row labeled s cube will be 4, 12 and 0. For convenience, we can also multiply this row by 1 over 4 and will complete the Routh table. Now all the entries in the first column are positive. In next slide, we will study about distribution of poles of Dear students, now we will study about location of poles when row of 0 occurs. A row of 0 occur in the Routh table when a purely even or purely odd polynomial is a factor of original polynomial. For example, s4 plus 5s square plus 7 is an even polynomial because it has only even powers of s. Now coming to the roots. Roots of the even polynomial are always symmetrical about the origin. And in this we have three possibilities. First is that roots of the polynomial are real. These roots will have position plus minus a on real axis as shown in the figure. Second possibility is that roots of the polynomial are on imaginary axis and symmetric about the origin. This is represented by location B in the figure. Third possibility is that roots are quadrantal, which means that the poles of the system will have an angle difference of. Dear students, now on the basis of roots of the quadratic polynomial, we will find out stability of the closed loop system with the help of Routh Hurwitz criteria. The roots of even polynomial can be either symmetric on real axis, can be either symmetric on imaginary axis, and can be quadrantal in S-plane. Now in example, the characteristic equation have order of 5, which means that this system have total of 5 poles. From first row to second row we have no sign change. From second row to third row we have no sign change, and the third row correspond to auxiliary polynomial. So which means that now onward we will test for even polynomial. From third row to fourth row we have no sign change. From fourth row to fifth, and similarly from fifth to sixth we have no sign change. If there exists a sign change after the auxiliary polynomial, then one pole will be in left half plane and second pole will be in the right half plane. As all entries are positive, so we don't have any right half plane pole. So our closed loop system is a stable system. Dear students, now we will further study about even polynomial. The j omega roots are symmetric about the origin. If we don't have any row of 0, then possibly we don't have any j omega roots. Everything from row containing the even polynomial down to the end of the Routh table is the test of even polynomial. The polynomial s power 5 plus 5s cube plus 7s is an example of odd polynomial because it has odd powers of s. Now odd polynomials are the product of even polynomial and an odd power of s. Thus the constant term of odd polynomial is always missing. Dear students, now we will study stability design with the help of Routh Hurwitz criteria. If we have an unknown parameter in the denominator of transfer function, and we know that denominator defines the location of poles, which directly affects the stability of a system. So with this method, we will find out range of values for which our closed loop system will be stable, marginally stable, and unstable. In this example, we have a closed loop system with unit feedback, which means that feedback path have gain of 1, means h of s equals 1, and forward path transfer function is given by g of s. Now first of all, we will find transfer function of closed loop system or characteristic equation of closed loop system. Characteristic equation is given by 1 plus g of s into h of s equals 0. Substituting the values and solving, we get characteristic equation s cube plus 6.5 s square plus 10s plus 10k equals 0. Now in this equation, as the k will vary, the location of closed loop system poles will also change accordingly. So for stable operation of the system, it is necessary to know the range of values for which our system will be stable. Dear students, now we will make Routh table with the help of characteristic equation. The characteristic equation has highest power of cube, so rows of the table will start from label s cube and end on s power 0, and we will place the coefficient according to the rules of the table. Now for stable operation of the system, there must be no sign change in the first column of the Routh table, which means that all values must be positive or greater than 0. In the first row we have 1, which is greater than 0. In second row we have 6.5, which is also greater than 0. In third row we have 65 minus 10k divided by 6.5, and in last row we have 10k. Now for stable operation, these both terms must be greater than 0, and we will get 10 multiplied by k greater than 0, which means that k will be greater than 0. And secondly, 65 minus 10k divided by 6.5 greater than 0, which means that 65 minus 10k is greater than 0 or k is less than 6.5. Now from these both two ranges, which is k is greater than 0 and k is less than 6.5, the range of values for which system will be stable is the intersection of these both ranges. So for closed loop stability, parameter k must be greater than 0 and less than 6.5. For marginal stability, k will be equal to 6.5, and for unstable operation, k must be less than 0 or k will be greater than 6.5. Now if any of you have any questions, please ask.